By integrating systems of rate equations, the transdermal compartmental absorption and transit, or TCAT model, in GastroPlus simulates the dynamics of topical and transdermal dosage forms and the dermatopharmacokinetics of compounds delivered from them. As part of an effort to expand the model's capability, we have developed case studies for several small molecules in gel and microemulsion formulations. Here we describe our work on the steroid clobetasol propionate. We simulated clinical results for Dermavate cream, an oil and water microemulsion formulation of clobetasol prescribed for the treatment of psoriasis and other inflammatory skin diseases. In the study by Bodenlentz et al., Dermavate cream was applied for 14 days under occlusion to lesional and healthy arm skin sites of psoriasis patients. Clobetasol propionate concentrations in dermis interstitial fluid were sampled continuously by open flow microperfusion on days 1 and 14. DOFM probe depths in the skin of study subjects were measured by ultrasound, with a mean depth of about 870 microns and a 95% confidence interval of 90 microns. After calibrating a baseline model, we explored the sensitivity of clobetasol propionate delivery to a range of formulation characteristics. So here the schematic of the DOFM setup. The formulation is shown in yellow. Stratum corneum, viable epidermis, and dermis skin layers, and subcutaneous tissue are shown. The DOFM probe is shown embedded in the dermis, and compounds dissolved in the interstitial fluid can partition into the perfusate that's pumped through the probe and collected for analysis. The TCAT model uses well-mixed compartments and diffusive exchange pathways to describe skin permeation following application of a formulation to the skin surface. Concentration gradients in the skin can be treated by dividing compartments into sublayers, and skin permeation can be linked to systemic PK models, either compartmental or physiologically based, via blood and lymph perfusion. Baseline values of the model input parameters were defined from publicly available experimental data, and we parameterized human arm skin and clobetasol propionate skin permeability using information and QSAR models built into the TCAT module. Here in figure 2, the schematic of the TCAT module showing the skin, actually the formulation and skin layer compartments, the pilosebaceous unit compartments. The arrows indicate pathways for partitioning and transport, and the connection to the rest of the body is shown through the blood and lymphatic perfusion. In Table 1, input parameters for the microemulsion itself and for clobetasol propionate solubility and diffusivity and the continuous and dispersed phases of the microemulsion are listed in the upper portion of the table. In the lower portion of the table, the clobetasol propionate permeabilities in the various skin layers, as well as the extent of clobetasol propionate binding to proteins in the viable epidermis and dermis are listed. Results of our baseline simulation, matched to the clinical dose and applied area, are shown in figure 3. Calculated unbound clobetasol propionate concentrations in dermis sublayer 14, corresponding to the mean skin depth of the DOFM probes, were within twofold of the measured values and tracked the initial rise in mean dermis concentrations fairly well. But the simulations also predicted protracted clobetasol propionate delivery, with a time to steady state of about 72 hours, by which time only about 0.5% of the applied dose had been absorbed into the skin. So here we are in figure 3, simulated clobetasol propionate concentration time profiles for dermis sublayers 12, 14, and 16 are shown here with the dotted lines. The DOFM results plotted as the filled circles. Sublayer 14 once again corresponds to the average DOFM probe depth, and sublayers 12 and sublayers 16 correspond to the outer limits of the 95% confidence interval on probe depth. Bodenlentz et al. Also reported values of dermis clobetasol propionate AUC from 0 to 24 hours on day 1 for individual subjects. These values are plotted in figure 4 versus probe depth in the skin, along with predicted clobetasol propionate AUC 0 to 24 hours for each dermis sublayer. Simulated values pass through the upper range of the observed values, but displayed a steeper slope than suggested by the clinical results. So once again here in figure 4, the DOFM results plotted as the filled circles, the simulated results, or simulated clobetasol propionate concentrations in the dermis skin layers 1, sublayers 1 through 20, shown by the red crosses. In addition to this, we estimated the contribution of the sebum hair pathways to AUC 0 to 24 hours to be about 20%. And we did this by taking the difference between the baseline simulation and a simulation in which these pilosebaceous pathways were excluded. 20% may seem like quite a large contribution for the sebum, but it's perhaps not surprising given the high hydrophobicity of clobetasol propionate. Turning to parameter sensitivity analyses, as hydrophobic excipients of the oil-water microemulsion are varied, clobetasol propionate solubility in the dispersed phase may change, that is, may increase or decrease. And we explored the implications of this for a range of plausible values of clobetasol propionate solubility. And this is captured by the partition coefficient of clobetasol propionate between the dispersed phase and a reference water phase. The lower limit of this range is defined by the vegetable oil water partition coefficient, and the upper limit on this range is defined by the octanol water partition coefficient for clobetasol propionate. Results are shown in figure 5. As the dispersed phase water partition coefficient increased, clobetasol solubility in the formulation as a whole also increased. And this reduces the clobetasol fractional saturation in the formulation, which is important because that's the driving force for skin permeation. Okay, so here in figure 5, as the clobetasol propionate solubility in the dispersed phase increased, we capture that through this dispersed phase water partition coefficient, so it increases from its baseline value of about 360, which is the vegetable oil water partition coefficient, increases about tenfold up to about 3160, which is the value of the octanol water partition coefficient for clobetasol propionate. And as we do this, you see that the predicted concentration time profiles for unbound clobetasol propionate in dermis sublayer 14 fall monotonically. Further analyses, which time and space don't permit us to show, indicated moderate dependence of dermis clobetasol propionate concentrations on the volume fraction of the dispersed phase and slight dependence on the diffusivity of clobetasol propionate in the continuous and dispersed phases of the formulation, and very slight dependence on the microstructure of the formulation as reflected by the dispersed phase droplet size distribution. And these latter results reflect the fact that clobetasol permeation through the skin is being controlled primarily by the stratum corneum. To summarize, using the TCAT model in GastroPlus, we developed a model of clobetasol propionate skin permeation, and through careful determination of input parameter values, the model simulated clinical data with reasonable accuracy. The limited clinical data precluded confirmation of the model over broader spatial and temporal ranges. Nonetheless, sensitivity analyses of formulation parameters indicated greater dependence of clobetasol propionate delivery on emulsion thermodynamics, that is, solubilities in the continuous and dispersed phases of the formulation, than on formulation kinetics or emulsion kinetics, that is, the diffusion coefficients of clobetasol propionate in the continuous and dispersed phases of the formulation, and greater dependence on emulsion thermodynamics than on a drug product microstructure, again, as reflected in the dispersed phase droplet size distribution. Thus, we feel this work exemplifies a role that modeling and simulation can play in the rational design of complex topical formulations. Quality by design, if you will. We'd like to acknowledge the funding support from the US FDA through the grant number listed here. And also like to say that the views expressed here do not necessarily reflect official policies of the DHHS, nor does any mention of trade names, commercial practices, or organizations imply endorsement by the United States government. Thank you for your attention, and I'll be happy to try to answer any questions you may have.
Thanks, Bill. We're right at time, but I am going to ask a quick question, which is along the lines of, so what would be the implications of your findings for development of a treatment for psoriasis?
Well, that's a good question, Kevin. I have to admit that I don't. One particularly relevant point to that is at what locus or loci within the skin do you need, therapeutic need to reach therapeutic concentrations of CP, of clobetasol propionate. And I have to admit that I haven't really done the, the pharmacokinetic background for the pharmacodynamic background for this. Whether those concentrations need to be in the dermis or they can be in the more superficial layers, the viable epidermis, the lower limit layers of the viable epidermis. I'm not sure. So the direct implications in terms of formulation development, not quite sure. But what the study really indicates is that given the physicochemical properties of clobetasol, in terms of these microemulsion formulations, you seem to have tremendous leeway in certain aspects of the formulation. That is the transport properties within the formulation itself, or the dispersed phase droplet size distribution are largely unimportant, which is due to the fact that concentration gradients that develop within the formulation relax on timescales that are much faster than the timescale for permeation through the stratum corneum.
Thank you. Unfortunately, it's a shame we can't continue this discussion. Please, for folks that have questions, please type them in the session chat window and or email Bill, and we will make sure that we get those answered for you. And with that, I will say thank you very much. And it's been a great first in human phase 1 session overall, and I am grateful for everybody coming and spending a good part of their day with us. So thank you very much and have a great rest of your day.
All right. Well, thank you, Kevin.